Welcome. So let's begin. Oh, thanks. So welcome. Let's begin. And there's 4 chapters left, and these are all to do with light. And we look at, first of all, we start by looking at the nature of light. Things like how fast does it go, and how does frequency relate to energy and stuff like that. It's a mixture of old things that we've learned and new things that we've learned. And then, and probably refraction and the like, you know. And then we start looking at using light to do stuff. So we start talking about ray diagrams. And very geometrical, there's a mathematical approach and there's a graphical approach. And then we start looking at interference of light. And then finally we end up with polarization and the like. So we go back to some extent to our knowledge of waves and interference of sound. There's some reminiscences of that as well. There used to be a big fight about was light a particle, the corpuscular group. And I think Newton was a member of that group. Or was light a wave, which is Huygens. And we don't argue about it anymore because it's kind of like a bit of both. In some cases, the wave nature is very important. In other cases, the particle nature dominates. I tend to be, I don't know if I'm being flippant or not, but I think of it like, imagine you work for Publix and you're told to put ravioli in the appropriate shelf. And you stand there and you go, is it pasta or is it dairy product? You know, because it's got cheese inside, but it's a pasta. So is it in the pasta aisle or is it on the cheese aisle? And it's like, you know, which is it? Well, it's a bit of both, you know. So you probably have a pasta aisle and you put it there, or maybe you put it somewhere else. But it's not the end of the world. Just because it's got 2 aspects to it does not mean to say it's an either or. You know, you can have things that are a bit of both. And there was clear evidence in Newton's time that light behaved like a wave, I think. And there's clear evidence that it behaved like a particle. And yet both groups seem to look at their own experience and just deny the other group's experience. You must be wrong because I'm right, kind of thing. So, for what it's worth, there is. Big ideas about the nature of light. Well, let's have a look. Energy of photons. So we think of light as photons, and you know, I'm not even sure what an electron looks like, so now I'm drawing a photon. But what I imagine is, I imagine a piece of ravioli, like, you know, with a little wave inside, and maybe that wave is sausage, or maybe that wave is cheese, or whatever. Well, maybe that wave is blue wave, or maybe that wave is a red wave, but it's a little bit, it's got a beginning and end. Well, it falls away to 0 each end, you know. Maybe it continues forever. And if you have different colored light, you'll have a different wave inside. And they will have different energies. So the energy depends upon the frequency, and the frequency tells you the color. I don't know how big the photon is, but the energy that that photon has. And we know E is equal to HF. So as the frequency gets bigger, the energy gets bigger because H is a constant called Planck's constant. Now, can anybody tell me off the top of their head, which is higher frequency? If I went, Richard of York gained battles in vain. So which is the highest frequency? Yeah, so this is high energy, and this is lower energy. Yeah? So it's ironic, isn't it? Because we think of cold as being cold as ice, and red has been red hot. But in photons, it's completely the other way around. And in fact, I know I don't know somebody, but I've seen a blog by somebody who basically goes around photographing things like hot water taps and cold water taps. And he's found a few which are labeled the right way, you know, which is like kind of weird, really. Why would anybody put hot as blue and cold as red? But he's got some photographs of somewhere in some wacky lab in the middle of nowhere in Antarctica kind of thing. They have the right color on them, yeah.
Is that an eye?
Red, orange, yellow, green, blue, indigo, violet. That's an eye.
Sir,
You said Roy G. Biv.
was indigo a color?
Yeah. It comes between blue and violet. So there's you know the story about that.
It's like Newton, right?
Yeah, Newton basically divided up into 7 bits because he wanted 7 bits. And so he something between blue and violet, so he didn't make up the color, but he kind of it's a bit obscure. You know, it's like, could I point indigo out? I'm not sure I could, but it's in the list, yeah.
Yes, sir. Well, you bring up a very good point as far as comparing, say, the glow of a flame and the supposed color of ice, although it's clear. And what I found is that it's comparing apples and oranges. If you compare a flame to itself, then you will notice that as you increase in the temperature,
It goes bluer. Yes. Yes, a Bunsen burner flame that's blue, watch out for a yellow one. Well, we'll still watch out for, but not as much. Yeah, that's exactly right. Just by the by, I had this discussion. So I worked on an instrument where they wanted to show intensity of signal on a color map. And our color maps they just were awkward, and I couldn't. And then finally I realized what it is that on our scale of intensity, my programmer had put blue as the most intense and red as the least intense. And when I kind of challenged him on it and said, why don't we have like red as the most intense like everybody else in the world? He said to me, but blue photons have more energy than red photons, which just struck me as being, it's one of those things where you're correct, but man, I want to just ask you, what on earth are you thinking, Because although literally you're correct, nobody does blue as the peaks and red as the troughs. It's just like we're all trained to interpret things just intuitively that way. Yeah.
sir, would think that red being a long wave would have further distance, and blue being a shorter wave, a more higher frequency.
High frequency.
Would have lesser oomph.
Oomph meaning?
Lesser, I guess, force is a word. In other words, if I project the blue and a red light's going to travel farther than the blue, I'm presuming.
No. They both travel forever until they're absorbed. Because they're both just ripples in the electromagnetic void. So now you might absorb one more than the other with particles or with water vapor, but they both travel from distant stars, and one doesn't run out of energy before the other.
Very good point.
Yeah, they'll both travel until they get absorbed by something.
I think I'm thinking of AM and FM frequencies then.
Okay. So we have this thing about the color. The speed of light is always 3 times 10 to the 8 meters per second. Reflected surfaces are specular or diffuse, and we'll talk about that. If you get a satin finish, if you want a satin finish on your chrome work, then it's diffuse. Specular reflectors obey the law of reflectivity. Well, yeah. So here we go in. So energy of a photon is related to Planck's constant, E equals hf. E is in joules. Planck's constant would be in joule seconds, and frequency is 1/seconds. It's hertz, but it's 1/seconds. Blue photon has more energy than a red photon, and this is the visualization. This is actually, I think, out of the book. They're clearly making a little package which is the same size in every case. And fair enough, I'm not going to argue about where you should draw the beginnings or where you should draw the ends or whatever. It's a decent way of thinking about it. How does energy relate to photon frequency? So E is equal to hf. And if I was to plot it as a graph, I'm not above asking you to do this. E and F, as the frequency gets bigger, the energy gets bigger and it's linear. So this is a linear relationship. What is the energy of a green photon? I'm sorry, I just got it in my head years ago that 400 nanometers is a green photon. Turns out it's blue. So what was I thinking? But what is the energy of a blue photon that has a wavelength of 400 nanometers? So E is equal to HF, which equals H, which I did not write down. Oh, there it is. 6.6 times 10 to the minus 34. So that's really small. 6.6 times 10 to the minus 34 times that frequency. Ah, no, not that frequency, that wavelength. Got to do a bit of work here, haven't I? Times the frequency. Well, frequency, C equals F lambda. Do you remember that? Speed is equal to how quickly you step times how long you step. Yeah. So that means that F is equal to C over lambda. Oh, so this is equal to H times C over lambda, which equals 6.6 times 10 to the minus 34. You don't need to know that number for the test. I just want you to see it every now and then so you know it's really small. Times speed of light, which is 3 times 10 to the 8, which is really big, but it's not that much bigger, you know. Minus 34 is really small over the wavelength, and the wavelength is 400 times 10 to the minus 9. Oh, dear me. So I need my trusty calculator, which, of course, oh, no, I have a bag. And if I have a bag, I have a calculator. Okay. So that's going to be 6.6 second EE to the minus 34, enter, times 3 second EE to the 8, enter, divided by 400 second EE to the minus 9, enter. That's going to be 4.9 times 10 to the minus 19. And what do you think the units are going to be? Joules. Yeah, you're in energy, so it's going to be joules. And that is really small. So a photon of light by itself, very low energy. But there's a lot of photons in anything that we can see. I mean, yeah, we're looking at a whole bunch of photons. Our eyes are getting energy from the environment, and we're getting a lot of photons at once. Cool. So, not bad. Bit of historical stuff. And I don't know, can you just, give me a quick show of hands? So, how many of you find historical background enjoyable? So sometimes.
It's a good story.
Yeah, yeah. How many of you just don't care at all about the historical background and just give me the equations and let me out of here? So for those 3 people who have not put their hand up.
Oh, I'm the second one, sorry. I'm not a big fan of background.
For those 2 people who've not communicated with me, what do you think?
50-50. Sometimes it's kind of cool, sometimes it's just, whatever.
Yeah, yeah. What do you think?
I don't really care if I...
You don't really care? Yeah, yeah, cool. Because, so when I was a student, I think because I was going to be tested on the equations, my sense was give me the equations, just get out of the way. But as I get older, I find the historical stuff is kind of helpful. It puts a face to an equation in a way and makes it much more approachable. And that's just casually looking at the history. But when you look at the actual detail of the history and you see how they struggled, the kind of turning point for me was I was reading, actually you can get Newton's original logbooks, you can read them. And you see him literally struggling for the word, because the word isn't in our language yet, and he's struggling to try and explain something. And there was this real sense of, oh my word, language matters. And here's this guy, and he's like, the genius that we're going to talk about 400 years later, 350 years later. And yet, he's like struggling for the word. And I just found that made it the whole game much more approachable to me. Yeah.
You know, if you just give us the equation like over and over again, you know, sometimes it seems like the equation just came out of the sky.
Yeah, that's right.
From the mountaintop.
Yeah, exactly.
You know,
Yeah.
Someone said this is, you know, there's no story behind it.
Yeah,
So,
that-
you know, occasionally, it can shed some light.
Yeah.
On, you know, not only, you know, that maybe the equation is credible.
Yeah.
But, you know, it came from a human.
Came from a person under certain circumstances because of certain interests. Yeah, I agree with that. Yeah. Cool. Yeah, you're kind of like, you're way ahead of me because I didn't get that for a long, long time. So here's a little bit of historical bit. So good old Roma, Ole Roma. So 1608, yeah, 1608, 1609, Galileo hears about the spyglass and makes himself a telescope. And like the first thing he does in the night is he looks at the moon. And he sees that the moon is not this perfect orb that Aristotle and all the textbooks say it should be, but it's got mountains and these circular kind of like craters. But as time passes and as the moon, well, as the earth spins, as the month goes by, he can see the shadows on the edge of these craters grow longer or shorter, depending upon which way the phase was going. And he realizes it's like looking down on the Alps. He's in Italy, looking down on a mountain range, how the sunshine, you know, on a morning, the valley is in shadow, but the mountain tops are in light. And then as the sun gets higher, then more and more of the valley gets in daylight. And he says, man, this is what I'm seeing in the moon. So the moon is got geography, topography, just like the earth. And that's completely counter to everything he'd been taught before. So that was kind of shocking. And then if you look now, 1675, the telescopes have been around for about 70 years, 65 years, you know, commonly good telescopes, been around for that length of time. And they're looking at Jupiter. Well, Galileo looked at Jupiter within a couple of weeks of inventing the telescope. He looked at Jupiter. And he saw these 4 specks of light in a line. And he thought they were stars. And he said to himself, man, that's weird. Those 4 stars are in a line. And he put it in his notebook, which we can read today. And then he looked like the next day and saw that they weren't in the same position. They were still in a line, but they'd all moved. And then he looked another day, there was 3 of them. And then he looked another day, and there's like back to 4 of them, but they're in different positions. So there's like a little bit of chaos going on. And he realizes, oh my word, they're not stars, you know, fixed in the night sky. They're moons going round Jupiter. And that was really revolutionary, because what that meant was that whereas the teaching of everybody, the textbooks, the government, the church, was that everything revolved around the earth, these things clearly are revolving around Jupiter. And that's basically saying this is the exception that proves your whole thing wrong. And it's in a way dangerous, and it's a way it's exciting. It's like so he comes out with that. He gets into big trouble. He gets house arrest for that and a couple of other things as well. But he gets house arrest. Luckily, he knew the Pope. They were buddies. That's why he thought he could publish it and get away with it, because his buddy was the Pope, but his buddy was like outmaneuvered and had to draw a line in the sand. If you ever watch television, sometimes the interviewer will try to get a politician to say yes or no to something in the future. And they dance around because they don't want to get forced into a corner. And that's what happened with the Pope. The Pope was basically, ignore him. And then people are saying, do you realize what he's saying? And do you realize how bad this is? And they're making the Pope have to take a side. Didn't really want to take a side. And eventually he does. And he puts him on how to burn him at the stake, which he could have done, doesn't. They showed him the instruments of torture. They said, do you really mean this? And he goes, no. Well, yes, but no, like that. And you go to your house and we'll let you know when you can come out. And he was there for 10 years kind of thing. Okay, so that's gone on. Roma, looking at the Io, one of the moons of Jupiter. And it's been observed enough that they know that the time for the eclipse of Io. Now, the eclipse is when you look from the Earth and you see Io kind of goes behind. It goes behind. So it's like that point there, when you go in behind. So Io goes behind and then reappears and comes around the front and then goes behind again. That time between going behind and going behind is 42.5 hours. It's only a couple of days, you know. Very fast, very, very fast. Our moon would take a month to do the equivalent, you know. So it's very, very fast. And, okay, so good telescopes to see that. I've got a decent telescope, and I can see the little spots, but seeing exactly when it goes behind, that's pretty good astronomy. And that was like, what, 300 years ago, 350 years ago that we're doing this. But here's what he notices. He notices that when you actually do it, like I want to just demonstrate to my class, I won't get 42.5 hours. I will get maybe a little less than 42.5 hours between now and the next time it eclipses. Or I might get a little bit more than 42.5 hours. But on average, it's 42.5. On average, when you add up all the periods and you divide by the number of trials, it comes out to 42.5. And he's thinking, why? And this is really kind of cool. What's happening is when the Earth is moving in its orbit and it's closing the gap between the Earth and Jupiter. Remember, Jupiter moves really slowly compared with the Earth. It's 5 times further away, yada, 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 or maybe 7 times further away, I can't remember. So it goes very slowly. And so when you're moving towards, you are moving towards. And the time taken for you to see the first eclipse is different for the time taken to you to see the second eclipse. Because the Earth has moved from there to there in that time. I'm exaggerating by quite a bit. So if I was to actually plot a graph and say, there's an eclipse, and 42 and a half hours later, there's an eclipse, and then 42 and a half hours later, there's an eclipse, and then 42 and a half hours later, there's an eclipse. In each case, if I could stand on the surface of Jupiter and say, now, if I was on Earth, it would not be now, it would be delayed by a little bit. And it would be delayed by a little bit because it takes time for the light signal to get to you. That was the first one. Now, for the second one, you're not so far away. You've moved towards, so there's less delay. And so rather than it been there, it's there. Didn't draw this very well. So rather than it been there, it's there. And this time is slightly less than 42 and a half hours. And that's because Earth is approaching. Now, if I do the same thing round here when Earth is receding, so there's my first measurement and here's my second measurement, then what I'll find is for my first measurement, there's not much of a delay. There is a little bit of delay, but not much of a delay. And for my second measurement, there's more of a delay. And so now I get what appears to be a longer period. And this is Earth recedes. I don't know how to spell recedes. So can you see the issue? So what we say is that Romer found that Io's periods were shorter when the Earth was approaching Jupiter and longer when the Earth was receding from Jupiter. Romer used the observations to calculate the speed of light was 2.1 times 10 to the 8 meters per second. And he was wrong, but he was only wrong because he had the wrong Earth orbital radius. Yeah, that was wrong. The textbook value he used for that, he didn't do that measurement. The textbook value he used for that was wrong. Otherwise, he'd have got a really quite a good number. So this is 1675. When did Christopher Columbus sail?
1492.
Oh, it was pretty after Columbus then. Yeah, a couple of hundred years after Columbus. But before the Revolutionary War. So
About 100 years before the Revolutionary War.
So when you guys were still part of, well, we were still part of Britain because I'm now an American. So, so pretty good, eh? And if that was in our science lab, we'd be relatively happy at, not that far out. It's in the right order of magnitude. But in Vom astronomy, is there anywhere we can measure it, like, if not in a room, at least on the Earth? And along comes Fizeau, 1850s, basically 160 odd years ago. And he does something really clever, and that is he shines a light through a wheel that has some gaps in it. The tendency is to talk about the teeth, because that's what you tend to form, these teeth with gaps in. But really the light goes through the gaps, so maybe we should talk about the gaps. So it just shines the light, and where there's a gap in front of the light can quickly escape and go and hit a mirror, and then the light can bounce back. So imagine that. So this is, I'm going to do my thumb and my finger as the gap. So what happens is the light goes through here, goes to the back of the room, comes back, and this hand is moving and hits my first finger. And I don't see anything. I see the light going away but not coming back because it hits the first finger. Well, I speed up. Now the light goes back, hits the back of the room, and because I've gone further, it's the second finger. Still not fast enough. Speed up. The light goes out through between the gap and it comes out and it hits my third finger. Go faster. Light comes out, hits my little finger. Go faster. Light goes out. Now I see the light. So when I get to a certain speed, I can see the light that I send out coming back. And if you go even faster, it'll start disappearing again, until it goes out through one and comes back through the second gap. But let's not worry about that. That's really fast. If you're going too slow, you don't see the light. If you're going faster, you don't see the light. If you're going faster, you don't see the light. If you're going faster, if you're going the right speed, you see the light. And I know that in the time it took the light to go from there to there, this thing went from there to there. So I can relate the rotation rate of the wheel to the time. So this becomes a timing device. So that's the game I'm playing. I say that my speed is equal to twice the distance to the mirror and from the mirror, so twice the distance over the time taken. And what I do is I say a toothed wheel chopped the light going to the mirror. The same wheel chopped the light on the way back. The rotation speed of the wheel was adjusted until light went out to the mirror through one tooth gap and returned through the next. And Fizeau found that it got 3.1 times 10 to the 8 meters per second. It's brilliant. Let's do a calculation on this. In Fizeau's experiment, the distance from the toothed wheel to the mirror was equal to in Fizeau's experiment, the distance from the toothed wheel to the mirror is 1 kilometer. 1 kilometer, which equals 1,000 meters. The wheel had 100 teeth, which means 100 gaps. There's always that question of, 100 teeth means 100 gaps. Not 101, not 99. 100 teeth. The wheel is spun 400 revs per second. then what's the speed? So the speed, c, is equal to 2 times d over t, which equals 2 times 1,000. Now, if it had one gap and it was going at 2 revolutions per second, it would be half a second for 1 revolution, yeah? If it had one tooth and it was going at 3 revolutions per second, it would be 1/3 of a second per revolution. Agreed? If it had one tooth, one gap, and it was 5 revolutions per second, each revolution would be 1/5 of a second. How am I getting the time for 1 revolution? What am I doing?
Calculating its period.
So what am I doing? I'm taking 1 second and I'm dividing it by
The number of revolutions.
the frequency, aren't I? Yeah, revs, yeah? So 1, we'll call this frequency equals 1 over the frequency, yes? Now, that's my time if I add 1 gap. If I have 5 gaps, does my time get longer or shorter? Same speed, but now I've got 5 gaps. Does my time get shorter or longer for the time between gaps? Shorter. How do I make my number shorter? I divide it by the number of teeth. Let's call this 1 over the revs divided by the number of teeth. Yep. So that would be 2,000 over 1 over, it was 400 divided by 100. So C is equal to 2,000 over 1 over 400. Dividing by that number makes it like that, which equals 2,000 times 400 times 100, yeah? So C in this case would be equal 8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the 7 meters per second. It's not the right answer, because if I give you the numbers to get the right answer, you know the answer. So this is, you know, a weird kind of place. But that's how he does it. And there's the answer. Now, so you take the distance traveled and you divide it for the time to go from there to there. And the more revs, the shorter that time, and the more teeth, the shorter that time. So they go on the bottom. Yep. In the textbook, sometimes you'll find they actually want to talk about the size of the gap versus the size of the tooth. So if this is like, if the tooth is half the distance, then you know that this is half, and so you know the time is 1/2. The bottom is going to be divided by a half, which gives you a bigger number. I think that's just, I don't worry about it.
I would think that we would use a piece of equipment off the shelf in some sort of mechanical device.
Yeah.
Which means the teeth would be the same.
Well, it depends. You can make. What I've seen in optical labs these days is they have very narrow gaps and very wide teeth, because that's really what you want from a resolution point of view.
Yes, sir. Forgive me. What I meant to say is that he would have picked up an item off the shelf, something relatively available. I would doubt that he would develop an apparatus.
Oh no, I think you did.
You did, you know?
I think so. Yeah.
Forgive me.
Yeah. No, those days they were like gentlemen scientists, and they'd build an elaborate apparatus. I mean, I don't know for sure, but you know. But anyway, so in the book, if you look at it, it'll seem more complicated because they have the duty cycle of the tooth, and I don't care about it. Okay. Cool. So not bad. 150 years ago, nailed it, you know. And then not along, but 350 years ago, along came Newton. I'm just reading actually a history of Hooke, Robert Hooke, Hooke's Law. Robert Hooke was about 7 years older than Newton. Robert Hooke was quite an influential person. He got well, it wasn't really a job, actually. He got to be the demonstrator at the Royal Society. Charles I had just been established on the throne of Britain, and some of the, powerful aristocrats had this idea about the Royal Society, so they had this idea about a society of scientists, and so they got a royal charter, and so it became the Royal Society. No money, because the king had no money at the time. He just fought a battle to get to be king, so he'd spent it all on soldiers. So no money, but they got the royal stamp. And so what do? They turn around to somebody and say, hey, we're going to give you the honor of being the demonstrator for the Royal Society. No money. But you're probably relatively well-to-do to begin with, or else you won't be talking to us, so, And that was the beginning of Hooke's career. His job was basically to come up with some demonstration every day, because these people liked to meet and they kind of wanted entertaining. So he had to build apparatus and, be a scientist for them. They weren't particularly good scientists for the most part. They were gentlemen scientists. They had their ideas and then just spread them. Not much of it was to do with experiments. But they were beginning to realize, after Galileo, that they needed experiments. And so 50 years before Galileo had really started doing experiments, and they were like, yeah, we need to do experiments. Yeah, we need to... Evidence-based, like in education now. Everything's evidence-based in education. It was the same. Evidence-based science. Problem is, when you've been raised on the other tradition, you have all this knowledge in your head that isn't evidence-based. And you're not going to throw it all out because it's evidence-based. And you're not going to redo all those experiments because you don't have time. So you still have all this information in your head that's not really necessarily true. So, but Hooke kind of like is the guy. And one of these Renaissance people, after the fire of London, helped Christopher Wren redesign London. Amazing things. An awful lot of stuff that Newton's famous for. He was like right there. Newton was 7 years younger than him. Newton was out in Cambridge. Newton was the bright prodigy that no one really knew about. And Newton, according to some people, kind of idealized Hooke. 7 years older than him, Hooke basically says, hey, we've got this Royal Society coming. The idea is you do research, you send it to us. We'll peer review it, just like they do now. We'll send you comments back. You get it all sorted out, we publish it, it gets printed. No more letters, it gets printed, distributed to the science community all over the world. It's like the internet. It's like somebody said, hey, we're going to get together in our club and you send stuff on, we're going to put it on the internet. You go, wow, we don't have to send letters anymore. No, it's on the internet. Anybody can log in. It's like, oh, this is revolutionary. So he did. And of course, who did Hooke give it to but the old guys who'd never done much experimenting in their life, who had all this knowledge that wasn't really right but was in the textbooks. And they shot him down. They kind of basically said, this is dumb, this cannot be right. And Newton was outraged. So Newton said, never again. I am not going to put myself in this. And basically did not send another manuscript in for the longest time. What he did instead was, he said, I remember my first expense account. I was working for a company. I had to give expense accounts in. So my first expense account, the guy I was following on from said, we'll split the bar tab for all these customers. And I wasn't sure if he was joking or not, because it was going to come to $200. And so I said, okay, so we split the bar tab. He took half the room, I took half the room. And I took my expense account back, and it had on there this tab for like $250. And my manager said, I'm glad to see you're taking this job seriously, and signed off on it without giving it a second look. I had claimed breakfast on the morning that I was flying out. And because I was flying out after like 10 o'clock in the morning, he argued that I could have had breakfast before I left home. So he lined out $5 for breakfast. So he signed off on $250, but he lined out $5. And it was like, it really stuck in my throat, this $5. So it ticked me off. And so I was reluctant to put another expense account in because there was going to be a fight, you know, because I felt like I had to say something, and yet, you know, because I couldn't let it go. And so my solution was I waited until the end of the financial year, and I gave him 5 expense accounts when he was busy, and he stamped them all. So the trade-off was I carried the account on my bank account for the best part of a year and then got all my money. I mean, it was not a wise move on my part. It'd have been much better getting the money early and leaving it in my bank rather than their bank. But, you know, that's the kind of thing you do when you get ticked off about things. And Newton, I'm not saying I'm the same as Newton, but Newton basically said, you don't like that paper? Fine. You're going to get a book from me. I'm going to give you everything. And then you argue with that. And so he didn't publish again until basically about 4 years later, and he produced this book. It's called Optics, a treatise on reflection, refraction, inflections and colours. And it's a tour de force. It goes on and on. You can find it at this Gutenberg press. It's got everything in it. And what's really remarkable is his diagrams. That's his diagram. I've grown up with an eye looking into the mirrors, and he drew the eyes. He was the one who came up with that way of presenting things. This could be out of our textbook. It's basically, it's there. And the language, it's his language. The symbols, it's his symbols. This guy just basically said, this is mine. It's not all right, but man, he basically made that his own. So a lot of what we learn is basically directly from Newton. So let's take a reflective surface. How do surfaces reflect? The photon comes in and somehow the photon gets reflected. Is it the same photon? Is it a different photon? With a piece of glass, does the photon work its way between all the atoms and then come out the other side? That photon, it's 400 nanometers. That's its wavelength. You know, I don't know how big the actual energy bundle is. I don't know, but it's like, man, and for much of this work, we don't care. It's like you can imagine it like a bouncing ball. You can imagine it like one ball bounces in, another ball bounces out. Doesn't matter. What matters is what he could see, which was when he took a polished metal surface, he found that the light ray comes in and it gets reflected, and these two angles are the same. And actually, even for a diffuse surface, where you get a roughed up surface, like maybe you use some sandpaper and you scratch up a surface, if you actually look in detail, he couldn't see this, but we know this now. If you look in detail, you'll see those angles reflect each other. But what happens is, because there's a whole different contour to the surface, it's not so even. So 1 does not become 1, 2 becoming 2, 3 becoming 3. 1 goes near it. 2 is way over there. 3 is way over there, and 4 is way over. There's a jumbling takes place with a diffuse surface. The image is diffused, if you like. So this is like a mirror finish, which is called a specular finish, and this is like a satin finish, which we call diffuse. If you take a mirror, and we'll do this in lab actually, if you take a mirror and you take pins, we'll do exactly his experiment, I think. and you look here, you'll see what appears to be a pin behind a pin. That's what you'll see. And then you put another pin there and another pin there. So all these 4 pins appear to be in line. And then you take the mirror away and you get a ruler and draw these lines up with the surface of the mirror. What you find is, if we take a surface normal, the angle of incidence equals the angle of reflection. Now, that angle also equals that angle, but that's not the angle of incidence or the angle of reflection. You tend to measure these angles with regard to the surface normal. And that's just the way it is. That's the way he decided, and we've inherited that tradition. There's no logical reason why it should be this way, but somebody had to pick, and he wrote the biggest book, so he got to pick, you know. So the angle of instance, that angle equals that angle. Yes, this angle also equals that angle, but they're not the angles we're talking about. So, and you know which one I'm going to give you. Okay, I'm going to give you this angle here and ask you about that angle there. So you be real careful, yeah. What he couldn't see was he couldn't see the wave nature of light, and he didn't even believe in it. Huygens believed in it, but he also couldn't see it. You can't see wave nature of light. So now, okay, what he could see was he could see that at an interface between, say, air, which is transparent, and glass, which is transparent, weird stuff happens. On one hand, the angle of incidence equals the angle of reflection, and again, here I'm talking about, I never thought about this, but that's really bad drawing by me. I know what I mean, but I'm not writing what I mean. That's the angle of incidence, that's angle of reflection. That still holds. It's not a very strong reflected ray. If you look at a piece of glass, you don't see a big, strong image of yourself. But it is there. But if you can see, you know, you can actually see this if you have a bright light, the angle that the light goes through the glass is typically closer to the normal. This refracted angle is not the same as the reflected angle or the incident angle. And that's called refraction. That's his term for it, refraction. Now, when you get back here, actually, just it's not on this diagram, but that ray there is the same, it's parallel to that ray there. So he could see this, and he could see that different transparent materials like water, glass, different types of glass, had different effects, different strengths of effect. Some of them not so much, some of them an awful lot. So there's something going on here. We now know that it's to do with, well, we now interpret it as it is something to do with a foreshortening of the wavelength as you go into some optically denser materials. So we can say the refractive index, this is a number of merit, it's a figure of merit for a material. So there'd be a N1 and an N2. And the N1 for vacuum is 1, no change. The N2, the N for, say, glass, might be 1.5. The N for diamond, 2.5. The N for air, for air, 1. The N for water, 1.3. They've got these various numbers. And what it's to do with is to do with the wavelength of the light in the different materials. So, whoa, what's going on here? Let's hold on. Yeah, sorry. Okay. So, if V equals F lambda, so your speed is equal to how many steps a second you take multiplied by the stride in each step. If v equals f lambda and I am going at a different speed, then either my f must be changing or my lambda must be changing or both. We associate frequency with colour, and the colour doesn't change. The colour of light doesn't change. And so the f is not changing, so that means the lambda is changing. So it's this light has a shorter wavelength in water than it does in vacuum. It has a shorter wavelength in diamond than it does in vacuum. It has a shorter wavelength in glass than it does in vacuum, which means it goes slower. Now, Newton couldn't measure that, but now we know. It's going slower. And we start building up a whole bunch of ways of visualizing the effect. And I'm going to show you one that good old Huygens came up with. So in order to describe, sorry, wrong way. In order to describe this effect, where you get this change of angle, what was going in that direction now changes to go in that direction. What Huygens did was he said, imagine a whole bunch of soldiers marching. And they're marching along a playground. That's 1 step, 2 steps, 3 steps, 4 steps. They're all in line. And then what happens is the soldier on this end starts stepping into sand. So he can't walk as fast in sand as you can on pavement. You know that. That's why they don't have sand for running tracks. You get tripped up by the, yeah? But you can move your legs just as fast, let's say. So what happens is this guy can't go as fast, but this guy can't go as far, but that guy can. And now this guy can't go as far, but that guy can. And now this guy can't go as far, but that guy can. And now this guy can't go as far, but that guy can. And so what happens now is these guys are going in that direction. And can you see how there's a difference in direction? I'm cheating now, aren't I? There's a difference in direction. And it's because of this effect. Well, it's not, light is not soldiers marching in line. So it's an analogy, isn't it? It's not really what's going on. And there's another one you see in the books where they have a kind of like an axle from a car. And they have the axle running towards it. And you kind of intuitively know that this end will catch and it'll go like that, you know? It's a way, again, there's not an axle inside the light. It's just an analogy. But it gives you this sense of you'll get a bending when you go from one interface to another. That's what it's basically talking about. But what we know is the real situation is there's a change in the speed of light between the different mediums. So we say, let's characterize this difference in the speed of light by a thing called the refractive index. And what we say is that the refractive index for a material is the speed of light in vacuum divided by the speed of light in the material. And because things only slow down, n is always bigger than 1. So we say light travels from one medium to another. Its frequency does not change, but its wavelength must change. We define the refractive index as the wavelength in the vacuum over the wavelength in the medium. Okay, so when I apply this, so I have an N1 for air, say, and an N2, say, for water. And I think about that angle of incidence and that angle of refraction. They are related to each other. They depend on the two refractive indices. They depend upon the incident angle, and you get what you get for the refractive angle. Refraction is the bending of light ray as it passes from a medium with one optical density to a medium with another optical density. Incident ray, refracted ray, and the refracted ray and the surface normal are all in the same plane. That just means it can't have a bending. It can't kind of come in like that and then bend over to the side. must be in a plane. This occurs because the speed of light is different for different media, and we say, that's true, but this is what I remember. This is Snell's law. I don't know if Snell was a scientist, I presume he was, but N1, the refractive index in 1, sine theta 1 is equal to refractive index in 2 sine theta 2. And that's just true. And we demonstrate that in lab. And these N values for diamond, very big. Crown glass, that's like crystal, quite big. Water, not so big. Air, basically just the same as vacuum. Glasses, you can buy cheap glasses and you can buy expensive glass, and they have different refractive indices. The reason why we like diamond rings is because they sparkle. And the reason why they sparkle is because they have a huge refractive index. And when you have a huge refractive index, a whole bunch of things happen. First of all, when the light comes in, its direction changes dramatically. And as we'll see in a minute, it separates the colors of white light a lot more. And so you can make the same shape of stone out of glass as you do out of diamond. Same angles. It will not look anywhere near as bright and reflective, as sparkly. And so we don't value it as much. It's like, man, look at that. That catches my eye. That's a diamond ring. That catches my eye. There's an interesting thing going on at the moment. So diamonds were not particularly, were not as ubiquitous. I'm going to stop here.